we will now derive another property for the components of stress tensor, which will help us to simplify the stress tensor. In this case, we take do a moment balance for the same geometry, and for the case of moment balance we need a axis of rotation, so that we can identify the lever arm for each of the force. Okay. So, let us do that. So, moment balance is what we are going to write. We take moments about an axis parallel to z axis at corner A. Okay. We have plane in the xyz axis and I had taken a z axis at corner A. Okay. So, this is a corner and your z axis is perpendicular to the plane of your slide. Okay. Now, let us write down the moment balance. We will have to account for the sign, the force and the perpendicular distance. 3 are to be accounted for each of them, and let it complete, then we will go term by term. Okay. And we consider clockwise as negative, anti-clockwise as positive. Okay. How do you assign clockwise, anti-clockwise? Let us say you have pivoted your plate here, and if you are considering, if you are focusing on one force, let us say that force deflects your plate in this direction, that is anti-clockwise, and then you pivot it, let us say that force deflects your plate in the clockwise, that is clockwise sense. Okay. That is how we identify the sign. Okay. Let us keep this in mind, and let us look at the sign of each. Okay. So, tau dash yx, tau dash yx. So, if you pivot it and then allow that force alone, it will rotate in the clockwise direction. Okay. That is why it is negative, anti-clockwise is positive. And what is the stress? Of course, tau dash yx. What is the area? The area is delta x into h, that is the area, delta x into h, that is the area. And then what is the lever arm, or the perpendicular distance is delta y from the axis A till that face, the distance is delta y. Okay. So, we multiplied the stress with the area to get the force and multiply with the perpendicular distance and taken the sense of rotation as well. Now, let us go to tau dash yy. Now, this will rotate in the anti-clockwise direction. If you pivot it here and allow this force, this will rotate in the anti-clockwise direction, and that is why this is positive. The stress value is tau dash yy, the area is delta x into h. Now, the perpendicular distance from here is delta x by 2. Okay. And let us go to the next term, tau yy. So, now this will rotate in the clockwise direction. If this is acting in this direction, if you pivot it here, this will rotate in the clockwise direction, and that is why you have a negative sign here. The area is delta x into h and perpendicular distance is delta x by 2. Okay. So, similarly you can explain other terms for tau xx, tau dash xy, and then tau dash xs. Okay. So, let us take one example, let us say tau xx is here. Okay. Of course, that will rotate in the anti-clockwise direction. So, positive, area is delta y into h, perpendicular distance is delta y by 2. Okay. And tau dash xy is this stress, and area is delta y into h, distance is delta x, and that is anti-clockwise, hence positive. And then tau dash xx is clockwise, area delta y h, distance is delta y by 2. Okay. Now, coming to the body force, we have Bx per unit volume. So, we multiply by volume, you get the force per unit volume, multiply volume, you get the force, and the distance is of course this distance. So, delta y by 2, and then Bx, if you leave the Bx, it rotates in the clockwise direction, that is why this is negative. Analogously, for the that due to the y direction body force, By multiplied by volume, perpendicular distance. Okay. That is a moment balance. Okay. Now, let us write that quickly, the moment balance here. Okay. Now, we will divide by delta x delta y h, that is the next step, is equal to 0, divide by delta x delta y h, h is thickness of the plate. Now what happens, here these three terms cancel, okay, and for tau dash y y we will consider these two terms, delta x cancels off, h cancels off, you are left with delta y in the denominator, okay, and you have this half here. So, half into delta x by delta y, and this is positive, this is negative, that is why I have written as taking this as common factor, tau dash y y minus tau y y into half delta x by delta y. Now if you take these two terms for tau x x and minus tau dash x x, those terms are written here. When you divide by delta x delta y h cancels away. So you are left with delta x in the denominator, of course delta y in the numerator. So you have half delta y by delta x, of course tau x x minus tau dash x x, and then of course other terms are as such. We already discussed about you have minus tau dash y x, other term is tau dash x y here, which of course other terms gets cancelled away, and then for the body force delta x delta y h, that cancels away, you are left with delta y by 2 and then delta x by 2. Okay. So those are the terms remaining after dividing. Now what should you do next? We are trying to find a relationship at a point. So as usual, take limit delta x tending to 0, delta y tending to 0, it becomes a point. Now as we have repeated several times, it becomes very evident here, you should keep the aspect ratio same. You should not say that delta x tends to 0, delta y tends to 0, it becomes indeterminate. We shrink the plate keeping the aspect ratio same. So this delta y delta x by delta y is a finite value till the final point to shrink to a point. So it becomes very clear in this example. In this particular case, we have done told this several times for control volume, surface, etc. Here there is a ratio of the dimensions of the length and width. You are shrinking this plate to a point and should always keep the aspect ratio. So delta x by delta y is a finite value till, even though both of them tends to 0. Okay. And as usual, when I write the moment balance, they are all average values, now they become point values. Okay. So now let us see what happens, how does it get simplified. So this is a finite term. We have proved in the earlier slide that tau dash y y is equal to tau y y. What are they? On the opposite side of this same surface, normal stress acting on the opposite side of the same surface. We have proved that they are equal and opposite. So these two will cancel and become 0. Similarly, these two terms along the x axis, tau x is equal to tau x x dash, that is what we proved earlier. So that term will also become 0. Now because delta x delta y tends to 0, these body terms also will not contribute. So what is left out are only the shear stress terms. Okay. Remember, this expression can be used only in the limit. Remember, when I wrote this expression, this equation, I have not used tau dash y y equal tau y y. Reason is that is average value. When I take limit delta x delta y tending to 0, it becomes point value, and we have proved that on opposite side of the face normal stresses are equal and opposite. So only when you take that limit, it becomes equal and you are using that result. Okay. So now all the terms vanishes, resulting in tau dash y x is equal to tau dash x y. What does it mean in terms of this diagram? Tau dash y x, this is equal to tau dash x y. Okay. Now we have taken this moment about A and proved that these two are same. So it is intuition, by intuition we can say that to prove others we should correspondingly take moments about other axis. So let us take moment about corner C, we take moment about corner C. So obviously we will prove that tau y x equal to tau x y. Okay. Now taking moments about corner B, if you take about corner B, then we will prove that tau dash x y equal to tau y x. Of course I will mark here, this is tau dash x y, this is tau x, both are same. Finally, taking moments about corner D, then we will prove that this tau dash y x is equal to tau x y. Eventually what happens, though there are 4 terms shown there, all of them are same, we have shown that if you take though I have drawn to begin with different variables, all of them have the same values, all of them are tau x y, that is all. Okay. What is the conclusion? Cross shears, that is shear stresses acting on adjacent faces at a point are equal. You have a point, you have to, earlier it was same face opposite side, now we have 2 adjacent faces. The why do we say cross shear? The normal to one face is y axis, normal to the other plane is x axis, that is why they are cross shears, one is tau x y, other is tau y x. So, cross shears acting on adjacent faces are equal, that is a conclusion. Okay. What is the implication of that? Stress tensor is symmetric, only 6 independent components, that is some relief for us, otherwise we have to deal with 9 stress tensor components. Thanks to this equality, thanks to the moment balance, that only 6 independent components. So, what are the 6 independent components? The normal stress components, of course, and among the 6 off diagonal elements we need to consider only 3 of them. Okay. Look at the way in which this stress tensor is written. Earlier we have written as all the 9 to be independent. Here these lower diagonal elements below the diagonal are written as same as those above the diagonal. Okay. So, in this stress tensor representation only 6 independent components are shown, 3 along the diagonal and only 3 off diagonal elements, not 6 off diagonal elements. Okay. Tau x, this is also tau x y, this is also tau x y, tau z x, tau z x, tau y z, tau y z. Okay. So, only 6 components have to be dealt with. Okay. Same thing can be extended to other planes as well. What we have discussed is these 4. Okay. Similarly, of course, representation from Parnas, that tau y z is equal to tau z y, that is what we have seen, and similarly these 2 on the opposite faces, tau z x is equal to tau x z, similarly opposite faces. Okay. Even the example which we have considered, the numerical example to illustrate stress element, we took only a symmetric stress tensor, though of course I did not really mention that time. Now we can recall saying that it is what a symmetric stress tensor. Okay. I think we had, if we recall back, we had I think minus 5, I think, and then minus 15, 0, 10, 0, 0, 0, etc. It was a symmetric stress. Okay. Even all the examples, etc., all the cases we will see only symmetric stress tensor. Okay. Now, what we have derived is under static condition, because under equilibrium condition, but whatever results we have seen are valid under dynamic conditions also, and that is what we are going to just mention here, not really prove. Okay, let us summarize what we have done. All the results whatever we discussed so far in this part, remember we started with Cauchy's formula. Okay. What did we do? We wrote a force balance. The force balance is shown here, and the right hand side was 0. All the time we took the right hand side to be 0. Okay. So, that was equal to 0, and next we proved that shear stresses acting on opposite sides of an interface at a point and normal stresses acting on opposite sides of an interface at a point are equal in value opposite direction. For that we use the force balance again. Of course, geometry is now different. For the case of Cauchy's formula, it was tetrahedron, now it is a 2-dimensional plate. Here again right hand side was 0. Now, for cross shears we proved that shear stress on adjacent plane adjacent faces at a point are equal, we wrote a moment balance. Again in the moment balance we took the right hand side to be 0. All these equations, the force balance with the right hand side 0, the moment balance right hand side 0 are all under static conditions. If you are writing the balance under dynamic conditions, what will you have on the right hand side? You will have a rate of change of term, okay, rate of change of momentum term, and then you will have rate of change of linear momentum for force balance, you will have rate of change of angular momentum for the momentum balance. Okay. But those terms are all proportional to volume, proportional to mass. And remember, when we took the limit delta x delta y tending to 0, these terms wherever you had body force, they were also proportional to volume, they never played a role in the final relationship. These terms never played role in the final relationship. So, even if you include the right hand side, the rate of change of linear momentum, rate of change of angular momentum, those being proportional to the volume or mass, they will not play a role. In the surface area you have some linear dimension squared, length into width or something, there you will have length, width and some thickness also is there, that is proportional to volume. When you shrink delta x delta y tending to 0, one linear dimension remains, and when you shrink to 0, that will vanish. Okay. So, those will not contribute. So, that is why we are not, just to avoid complexity, we are just mentioning, we are not taken that into account in the derivation, but intuitively reasoning out we can understand. So, derived for static condition, valid on dynamic condition also. Okay. We have discussed the rate of change of linear angular momentum proportional to the volume of element will vanish in the limit delta x delta y tending to 0. Okay. So, we should not assume or come to the conclusion that these results are valid only under static condition, they are certainly valid under dynamic conditions also. Okay. That is the key thing I have to say. Okay. So, let us summarize. We derived a relationship between the stress vector and stress tensor, namely the Cauchy's formula, simple force balance. So, now we should know what is that relationship, simply writing a force balance. And we also discussed what do we mean by stress at a point conceptually. It has all the information for finding out stress vector on any plane. We looked at numerical example, represent that in terms of 3D representation in terms of vectors. And then we arrived at the properties of stress tensor. First is that opposite sides of interface, the shear stresses and the normal stresses are equal and opposite. Okay. And we also discussed about equality of cross shears. Okay. To adjacent planes, the shear stresses are equal. Important conclusion is that the stress tensor is symmetric, that is the most important takeaway from the second property. Okay. So, this brings us to the close of our first visit to solid mechanics. In terms of our journey to the Navier-Stokes equation, we started with the Newton's second law of motion, applied the Reynolds transport theorem and derived the integral form of linear momentum balance. We applied that for a small control volume, derived the differential form of linear momentum balance, the left hand side and the gravity on the right hand side. And we had surface forces on the right hand side. To understand surface forces, we took a diversion to solid mechanics, and now this highlighted box is very clear to us. We discussed about stress vector, stress tensor, the relationship between the two and the properties of stress tensor. To summarize whatever I discussed during the first visit to solid mechanics, these are the topics which we discussed. we defined a stress vector force acting on a given surface per unit area. We discuss about a stress tensor, and a stress tensor has 9 components, and these are the components of stress vector acting on 3 planes parallel to the 3 coordinate planes. We also discuss about the sign convention for the components of stress tensor, and then we related the stress vector to the stress tensor by the Cauchy's formula, and hence discussed the state of stress as stress at a point. We derive the properties of stress tensor. What are the properties? On the opposite sides of an interface, the normal and the shear stresses are equal, but opposite in direction. And we also proved by using a moment balance that the cross shears are equal, which means that the stress tensor is symmetric.